All right, today we're going to talk about correlations and also regression, linear regression, which when we have a correlation, we can use to predict values. So let's remind ourselves what a correlation is. So when you have two features that are related to each other, this is called a correlation. For example, when looking at real estate, the price of the house is often correlated with the size of the house. A bigger house often will sell for more money, a smaller house for less money. Now, it's not always true, but in general, it is true. And so, again, we're looking at a general trend between these, and we call this a correlation. Here, we often use scatter plots where we plot these two values against each other, and then we look for a relationship the way these plots kind of lay out to see this. And the simplest examples of this is a linear relationship where we kind of draw a straight line to define how they're related. The strength of a correlation is measured by its correlation coefficient. This is the number between -1 and +1. So values about at like +1 show that they're positively related. So as a size of the house goes up, the price of the house also goes up. And so you see that. A negative coefficient, -1, means they are correlated, but in opposite things. Maybe the number of crimes in the neighborhood and the price of the house. As the number of crimes in the neighborhood goes up, the price of the house might go down there. So that's a negative correlation. But again, still a correlation. When you don't have a correlation, the coefficient is around 0 here. So here's some examples here where you can see this line. So this might be, this little thing shows a scatter plot. Here I'm going to zoom in on this little graph a little better. This might show a scatter plot. So like, look at this plot here. This might be on the x-axis prices of houses, and on the y-axis the size of the house. And then we'll see that houses that are generally smaller in size down here are also smaller in prices. And houses that are maybe bigger in size are bigger in prices. But this isn't a very good correlation. This is a better correlation where we see a much more general line here where, again, smaller houses, smaller prices, larger houses, larger prices. When we go larger on the x-axis, the data also tends to go larger on the y-axis up here. And this would be the opposite, a negative correlation where, again, maybe we're looking at the number of crimes in a neighborhood and then the price of a house. So as the number of crimes go up, the price of the house actually goes down here. We get more houses here. Now, again, not all houses follow this pattern. There are some different things, but it shows a general trend or correlation here. Now, if this is a very tight correlation, we get much more of a line like this or like this. But here, this is even a correlation, just not, we can get some information of this, but just it's not as obvious of a correlation. There's many more outliers. Not every data fits this point here. And this is actually where no correlation here. So, and again, the slope of the line doesn't matter, just if it's positive or negative. So these are all -1s here, and these are all positive ones on this side. So the slope of this line doesn't matter, just how tightly the data points follow a line for this. Now they have to follow a line, they can't be other patterns, so these are not correlated with our linear correlation models for this here. So one thing to remember, and this we repeat this in all statistical courses and stuff, is that correlation is not causation. So just because two things are correlated doesn't mean that one causes the other or vice versa. Some other possibilities that is that relationships between the variables is just a coincidence there. We'll look at some of those in just a sec. There can be reverse causality. Sometimes we think one thing causes the other one. In reality, it's the other way around. The first item causes the second item, or is somehow related there. And what's more often a problem is that we have a common, what we call a confounding variable that causes both events here. And so we see that. So an example might be there's a strong correlation in the United States between the number of people eating ice cream cones and shark attacks. As more people eat ice cream cones during the year, uh, we have many more shark attacks here. And so you can think maybe there's a cause, and you're wondering which way does that cause go? Does eating ice cream make you taste better to sharks and lead to more shark attacks, or do the fear of shark attacks make more people eat ice cream? You don't know. Well, it's you don't generally neither, because again, there's this confounding variable here. Summer, the heat, the fact that more people are out in the summer causes both, or it was related to more events rather than one causing the other. So that's there are some interesting examples here of causations, not or correlations not implying causations. There's a couple articles here that you can go through and read for more examples of this. There's some kind of fun ones in this, so I suggest glancing at those. Let's look at some examples of correlations and how we might see it. First, what I'm going to do is this learning practice 2, which we did last unit. So in this, we were looking at the iris data set. And if you remember, there were 4 different features in the iris data set. There was the sepal length and the sepal width and the petal length and the petal width. So with our iris followers, we had these sepals and these petals here. And we have lengths and width of each. And we were plotting them both out and looking at some graphs. So let's scroll down here. So here's a graph of the petal length versus the petal width. And this is a scatter plot of those 2 things. So you can see here's one flower with a very small petal length and a very small petal width. And here's another flower. This has a petal length of about 4 and a petal width of about 1.4 maybe here. And then up here, these are much larger. This one has a petal length of about 6 and then a petal width of about 2.5 up here to maybe 2.25 down here. Example. So we're just plotting. So each of these dots is a different flower, and it shows both the petal length and width. And then we can see this correlation that as the petals get longer, they also tend to get wider here. So we have this very nice correlation that's drawn up here. And it's a positive correlation. As one gets bigger, the other gets bigger here. So this is an example of a correlation between these 2 things. And we can see other data like this. Now this, not so much of a correlation. So this is sepal length depending on sepal width. You'd think that would be similar, but this data is much more spread out. We don't see an obvious line. We kind of see a little bit with this chunk of data here and a little bit here, but again, it is really quite spread out. So if there is a correlation here, it certainly is not as strong. The correlation coefficient would be close to 0 with this one. This looks like this is again the petal length and width, much stronger correlation. This one not. Now it'd be interesting to plot these things out with different things, because there might be a correlation in each species of flowers. So we may have to break these species up to get a better view of this. So here's an example of that. So within this one species of flower, there seems to be a pretty good correlation. And again, with the orange species, the versicolor species, a pretty good correlation here. So again, sometimes you might have to break the data up to see the correlations better. I'm going to go down to the end here, and this is a common graph where we're trying to look for correlations. And here we're showing a bunch of these scatter plots here. So we're showing the sepal length depending on the petal width, the sepal length depending on the petal length, the sepal length depending on the petal width. Now, when we look at the sepal length depending on the sepal width, I mean, the 2 of the same things, that is an obvious correlation. I mean, there's only one variable there, so we're using a different graph for that here. But on these, we're doing scatter plots, so we can kind of see where there are correlations. So this looks like a pretty strong correlation. This is a little weaker correlation. This is a pretty weak correlation here. One thing to note on these graphs, often we only plot half of them because these are mirrored. So this graph and this graph will mirror each other. And again, this graph will mirror each other. Just the x and y axes are flipped for this. Same with this. So. Okay, so that's a little bit of correlation with that data. Let's look at some other data. Let's look at average temperature versus sunspot data here. This is a notebook on a website called Kaggle, which we'll use for often getting data and data competitions, and people will post their own examples of this. So I haven't checked out the data here. It seems like that it's getting it correctly, but I haven't done a lot of research into this data set, but I just wanted to use this as an example of showing correlations in Python. So again, I'm going to skip through all this where the person is laying out this data. What they're asking is that is there a correlation between average temperature, annual temperature, and the amount of CO2, related to global warming? And some people say it should be more related to sunspots or the amount of sun that's out there. So which is the temperature correlated with either of these two things? So we read in some data. Now there's actually quite a bit of parsing of this data. We have to read in monthly data, and then the monthly data gets temperatures gets averaged into an annual temperature, and those annual temperature is we bring in some sunspot data by year, and we have to combine that in the same data frame with our temperature data, and same with the CO2 data. So here's actually the sunspot data over the years. It actually tends to follow, I think it's a 12-year cycle of ups and downs here. And then again, here's the carbon dioxide, the CO2 levels here, and showing that that's increasing over the years. And then we're going to try to graph the relationship. So here's the relationship between annual carbon dioxide measurements and annual temperature readings here. And we do see a pretty strong relationship there, a correlation between those. And this is the sunspot data and the temperature. And there's a little bit of a correlation maybe, but it is one of the things you watch with correlations is that the slope of this graph is very flat. And so that tends to say there's not a whole lot of correlation, and also that this is spread out a lot. So the correlation coefficient will be very low, and the slope is also very flat here. So there's not really a correlation between sunspot data and average annual temperature for this. Another thing sometimes we'll look at with data is a heat map of this data. And so here's a heat map showing this. Now this is showing the, again, this correlation coefficient in a grid here. And so again, the diagonals are just the average temperature is always, exactly correlated with the average temperature. These are exact same numbers. So these values are always 1 along this diagonal going this direction. But again, you can now look at the average temperature correlated with the sunspot data, and that's very low, very close to 0 here. The average temperature correlated with the carbon dioxide levels, that is much stronger here, maybe 0.7 or 0.8 here. Even the average temperature correlated with the year is pretty strong, because in the recent years, as the years get higher, the average temperature is getting higher. And again, you can look at the temperature here and the year and how it's correlated with the other items here. So this is sometimes called a correlation chart or a heat chart, heat map, and it shows this sort of data. Now back to the iris data, I actually added a heat map to that. Besides this, this is the heat map for that. Let me zoom out just a little bit here. Here we can see the correlations. Again, you watch the numbers. So negative or +1 is kind of a dark purple. A negative correlation, it's only going down to 4 here. So that's still not a strong correlation. And wider values here are not correlated. So you can see things that aren't correlated so well or things that are. So certainly, again, along the diagonal, everything's correlated with itself. If I look at the sepal length and the sepal length, they're exactly correlated. But the sepal width and the sepal length are not very well correlated. But like the petal length and the petal width here, these two are very correlated, almost as much as the petal width length with itself here. So again, this is a heat map sometimes used to show these, and sometimes you can actually display them, and they'll actually put the correlation values in the graph to display that rather than just colors also, or some combination of those. So that's a kind of overview of correlations. If you think you know it pretty well, you might want to try this correlation, guessing correlation example. This is a little graph or a little challenge here. They have 4 different correlation or scatter plots and 4 different numbers, and so your job is to identify which of the correlation is a plus 0.9. So that's a pretty positive slope to the right, and it's pretty thing. So I think this is the 0.9. The 0.6, that's again positive but not so significant. I'm saying that's 0.6 minus 0.3 minus 0.8. I think this is the 0.8 and this is the 0.3. And then you can check your answers here. And then again, you can reload this and get different values for different things. So, and then try to guess, see if you can come up with all the right answers. So try that. Try to check out your readings on correlations here. So that's this guessing correlations here. Now, once we have a correlation, especially if it's strong, if we have a strong positive or negative correlation, we can then use it to predict values. The simplest way is what we call simple linear regression, where we have this scatter plot like this. We try to find the best line that we can draw in here that'll minimize the distance to all the points here. We call these values the residue, the difference between the line and the points, and we calculate lots of lines and figure out where we have the smallest residue or error for all the points. So here we're finding some line through that looks pretty good. Now once we knew this line, then we can use that line to do some prediction. So we can say, well, if our value is a value of 6, we can predict the output to be around 25 on that line here. Now this works well when we are predicting one variable and we're using just one other variable. So maybe we're predicting or the price of a house given the size of the house, and we fit that using a line here. But what if you want to use multiple variables? We do have a multiple linear regression where, again, we're trying to predict one value. In our linear exercise, we'll be predicting house values. But we'll predict them with multiple things, maybe the size of the lot, the size of the house in square feet, the number of bathrooms, things like that. So we use a number of variables and we'll predict one. So this is called multiple linear regression, and we actually we create not a line but a plane, and this plane is often in multiple dimensions, so we call it a hyperplane. And it's just hard to visualize hyperplanes in 5 dimensions and stuff. So we just let the math take care of that. But again, it's just analogous to this. It is just done in more dimensions with more factors, more variables to look at. Now, sometimes our relationship is nonlinear. This looks more like a curve. Now, we can fit this, we can do linear regression here, but it may not be the best estimate. So there are times where we want to do a nonlinear analysis. And again, this gets a little more complicated because we have to often limit ourselves to what kind of curve. So I have to kind of guess what kind of curve this is and then do a nonlinear analysis with curves of that type here. So we're not going to get into nonlinear regression here, but just know that it is. And in this example, we're just predicting one variable using one other variable, but we're fitting it not to a line, but to a curve. So once we have linear regression, once we can calculate this line here or this plane or whatever, then we can make predictions. So again, here's the average temperature versus carbon dioxide level if we're wanted to make a prediction. So what if the average temperature was 12.5 degrees Celsius? So that would be right here. What would you predict the CO2 levels to be? So you'd look up to this line and you say that looks like around here between 380 and 400, maybe 390 values here. So you can predict that. And again, I just approximated with the graph of once we have the equation of this line, we can use simple math to calculate these values. Just feed this value into our equation and get a prediction out of it. So there's some additional resources if you want to learn more about this stuff. So these are a couple additional resources you might want to look at that will give you more information about regression and cause and effect and that sort of stuff. So, okay, that's a quick summary of this week's topic.